Okay. Hi, everyone. I think we can slowly start. So welcome. I'm really happy that you decided to join this session and to learn a little bit more about AI, but from a little bit different perspective than of what currently the whole AI discussion is about. So today we're not going to talk about LLMs, but instead we're going to talk about something different, but in my opinion also super important and very interesting, which is continual learning. And today I would like to explain to you what is continual learning via a 3.5-act story, where you're also going to see what it is, how it can be used also in practice, using a use case that we implemented in the medical field. But as this is the first NDC for me, and for sure a first event standing on a floating stage, I would like to introduce myself first. So my name is Agata Chudzińska, and as my name is suggesting, I'm Polish. And this is the picture of me smiling in Polish, so we are laughing that this is a little bit, especially if you're on the streets in Poland, that's the way how we smile. I mean, we're not angry, we're just like behaving this way. But I'm working currently for a German company. It's called the Blue AI, and it's an AI consultancy company where I'm the CTO and AI solutions architect, so you can see me smile a little bit more. I have been working implementing the AI-based projects over the last 8 years, even more 9 right now. And I have worked with really a lot of different companies, starting from small startups to bigger companies like also BMW and others. But I think what will be more important for this session is that during this time I've also worked, and me and my team, quite a lot with the medtech companies, implementing projects in the healthcare area. But if I'm talking about that, what do I mean exactly? So in this area we have been mainly implementing projects around medical segmentations of the images. So we can think about it as finding the structures on the medical images, such as bones. For one of our last projects, which was segmenting the liver, but more importantly, with all of the veins in the liver, which are super important for the liver resection. So if you cut in the wrong place, it can have really bad consequences for the patients, unfortunately. And usually we also implement it in an extended reality way, so using MetaQuest or Microsoft HoloLens when they're still supported, or Apple Vision Pro, sometimes with additional measurements to support the doctors in the surgical planning or to conduct the patient education. But today I would like to talk a little bit more about one of our most challenging tasks in this area, which was connected with focal cortical dysplasias. But before we dive deeper into the project itself, I would like to draw your attention to some statistics that, according to me, are very important and quite surprising, but I didn't hear of them before I started working on this project, which are that it is estimated that about 50 million people worldwide, or according to different statistics, even up to 1% of the global population have epilepsy, which is making it one of the most important neurological diseases globally. And if it wouldn't be enough that the first thing that you think about epilepsy is having epileptic seizures, so these patients also have 24 higher chances, 24 times more likely to die unexpectedly because of a phenomenon called SUDEP, meaning sudden unexpected death in epilepsy patients. So I think we can all agree that this problem is really important from the perspective of the whole society. So if you would like to get a little bit more into this topic, sooner or later we will get to something called focal cortical dysplasias, or FCDs in short. And so something that look like that. So what are those FCDs? If we take a magnifier glass, they will look like that. So as you can see, there are some misbuildings of the brain, some errors in brain development, which have very high epileptogenic potential, meaning that they very frequently cause epilepsies. And fortunately for some people, they can just take drugs and live normal life. but some of them cannot. So they have the so-called pharmacoresistant epilepsies. And for more than 70% of them, FCDs are the reasons for them. The good news here is that they are potentially operable, but the tricky part here is to find them. So let's analyze how do they look like on MRIs. If you're above 30, you probably had at some point in your life an MRI already, but if not, if you're happy enough to not have to, let's have a quick recap of what MRIs are. So MRIs stand for magnetic resonance imaging. So this is a series of images that is being done by MRI scanners that can look like that or a little bit differently depending on the producer. But they create a series of images, like 50, 100, 200 images. And it's basically the scanner where you go into, it makes loud, strange noises. It's not quite well experienced if you are claustrophobic, but yeah, it really creates good quality images using magnets and radio frequency. And depending on different settings, they're exposing a little bit different features of our inner organs. So let's assume we have this MRI already. So let's take a look how do FCDs look like on the MRIs. So we have a set of features that can be present in there. One of the most important ones is the blurring between the boundary between the white and gray matter. Another one is cortex thickening. Another is unusual surface folding, so the duration of the brain is a little bit strange. Some hyperintensities, either of white or gray matter, or something that you can see on this picture, which is quite characteristic, visible path toward the ventricle, which you can see here. But to not make it too easy, they very frequently blend into the surrounding tissues. And this is not like the full list of the features that can be there. And also there are different combinations. Like it doesn't mean we have 5 features and we are just hacking, okay, these are the 5, this is FCD. Unfortunately not, so the combinations can vary. So these are just some of the features that can lead us that it can be an FCD. And they can also differ in size, in locations, and in shape. But when things go well, meaning that usually epileptologists, but sometimes also neurologists find an FCD, the patients can undergo a brain surgery, which looks more or less like that, and then the patient can become seizure-free. So that sounds really great for the patients. So we have learned already quite a lot about FCDs, so I have a task for you now. We are seeing here 3 different patients. And having all of that knowledge that you already collected during this session, I would like you to tell me if any of these patients, and if yes, which one, has an FCD. So a few seconds for you, and if you have any thoughts on that. Any ideas? Yeah, we have number 1 as a guess. Yeah. So that was a tricky one because all of them have. But usually, as you can imagine, and usually when you are reading some books about what are some features of, for example, some illnesses, the reality is not so easy. Meaning, these examples are not so obvious like the features that we have also talked about before. So the task usually requires very experienced epileptologists having like 20, 30 years of experience so that they can see really these features. Like we have worked with that months or even years, and even after that time, ourselves, we're not able to detect where actually this FCD is present or not. And as you can imagine, with very niche knowledge, which requires quite many expertise, there are not so many people who can do it, which results in the fact that the majority of the patients, they never get diagnosed properly and they never have the FCD removed. So we had an idea. Like, if you think about this thoroughly, there is some very subtle pattern in the data that is very difficult to detect for the human, but we know that it exists. And there are also some of the experts, but not so many, and we have very big benefits if we could democratize this knowledge. So we said, yeah, let's take this challenge and let's try to use AI to detect the FCDs. So we have taken some of our team members to work on the project. We cooperated with the biggest epilepsy center in Germany, which is in Hamburg. And we have even taken the real doctor house to make our chances of the project to be higher. And we started with the data set. Whenever you want to develop a good machine learning model, the data is king. You really need to focus on this part. So we managed to collect 201 MRI series, each of them consisting of almost 200 images, with FCDs. And to that point, that was actually, according to our knowledge, the biggest data set of FCDs in the world at that particular moment in time. But we didn't want to only say, knowing that there is somewhere FCD, to detect where it is. We wanted to be useful in the daily life. So we also have taken 100 normal MRIs, as well as 50 MRIs with different pathologies, because whenever you go to the neurologist, you can have some different things and not have like fully healthy brain. I told you about the different settings of the MRI scan. So in our case, we use the T1 and FLAIR. So there are three main, most popular and most important sequences type, which are T1, which is focusing on the shapes, T2, which is focusing on the fluids, and FLAIR, which is focusing on finding some abnormalities in the fluid. So it is like a special part, a special version of the T2 sequence. But as I said, we wanted to be as close as possible to the reality, so we've also taken all of the MRIs that were of suboptimal quality, meaning someone moved a little bit, like something happened to the scanner. I mean, things happen. So we also wanted to be included in our data set. And we also wanted to be extremely sure that really we teach the model based on the really good data, meaning that we have analyzed it by a few epileptologists. We have analyzed the type of seizures that people were having, as well as the EEG data, so these electrodes that are measuring your brain activity. One important point when you're working with the data is the ground truth. So I think this is also one of the reasons why there are not so many big data sets of FCDs before, which is annotating this data is really difficult. Here you can see a picture of how the annotation, so how did the expert tell the model that this is a person with FCD? So they were just manually annotating the region in which the FCD was present. Of course, we can make it a little bit easier via semi-automated methods if we already have some of them, but it's still very time-consuming and it really requires a lot of work. So yeah, we have our data set, so let's train our model, right? Well, not so easy. I mean, I would have lied if I said that we didn't try that. But it turns out if you have like a very complicated problem in machine learning and not so extremely big data set, it can be that the neural networks will not manage to find this pattern. So we can make the life for them a little bit easier using pre-processing methods. So in our case, we did that, and we did that in 3 steps. First of them was the brain tissue segmentation. So this is quite solvable problem, so we can achieve like very, very high accuracy on this issue. There is like no novelty in here. So we just use like one of the existing approaches. But why did we do that? So first of all, we just wanted to remove the unnecessary data, like for example, skull or other things. There is no impact of them for detecting FCDs. But more importantly, we did that so that we could go to the step number 2, which is using morphometric analysis. So it turns out that over the years, the epileptologists wanted to make their life a little bit easier. So they came up with additional methods that are exposing some of the features of FCDs. And one of them is the method developed by Dr. Hoopers. And we used 2 kind of features that he came up with. So first of them is junction, which you can see on the left-hand side picture, which is using this white and gray mirror mask, so the thing that we did in the first step, so that we can calculate the mean and standard deviations of the intensities to expose a little bit these features. And the other one, quite interesting, is that it turns out that when you apply additional blurring to something that was slightly blurring at the beginning, it will expose this feature even more. I was lately in one of cybersecurity talks and also learned that this is a very similar technique to what you can use to see which of the pictures and where have been changed in Photoshop or whatever. So it's quite interesting that it's just via applying additional blur. And finally, we have prepared our inputs. So we have right now the 4 channels, meaning the T1 flare. We also have the junction and extension, and we applied standard methods in machine learning, such as padding, cropping, etc. So now is the moment when we can go to training our machine learning model. So we have really trained a lot of different architectures. I will not go into details in here, but I want to show you the architecture that was winning for us, which looks in short like that. So this is a variation of very popular neural network architecture when it comes to biomedical imaging, which is sometimes called, which is encoder-decoder, or sometimes called also UNet, because it's having the U shape in there. So each of this block has additional layers. If you're interested in that, I will share a link at the end of the presentation. But just in very short to explain to you how does an encoder-encoder architecture look like. So it relies on the mechanism in which we have our input, in here the 4 channels that we have. And in the first way, so in the first part of the U, we are condensing a bit the information that we have, meaning that from the big picture, we are trying to make quite small representations, but with super many channels. And it is storing the information that the model thinks are crucial. Like, it's very condensed information about edges, shapes, etc. It's quite abstract. So that from this bottleneck, in the second part of the U, we are trying to get this information back. So either via creating the same image or via just getting some parts that are especially important to us, like in this case, quite huge FCD. And it turns out that by this process, the model is really able to get the super important features that are for our goal, which are the FCDs in here. In our case, we also use the variation decoder, which you can see below. This is actually not doing anything towards getting our results. It just makes sure that during the training, our model is not overfitting, meaning that it's not learning by heart the examples that we have shown it, but that it will also be able to generalize in the future. So let's take a brief look at the metrics and the results. So we have analyzed it from 2 perspectives. So first of them is quite classical, meaning that we have looked at the object-wise, like precision recall, so how many times we're right, did we create too many false positives. And the second one, which is quite interesting, is the voxel-wise metric. So we can think of voxel-wise like pixels is in 2D, then voxel is the same concept but in 3D. And we have applied here the dice coefficients. Why is it so important? Because we're looking at not only if the model thinks that there is FCD in there, but also where exactly. So it has really a strong power when it comes to the explainability of the model. So we did quite many experiments, but just the best one that we achieved, we can see here. So we can see that we are able to detect about 70% of the FCDs correctly, which is quite good results, assuming how difficult the issue is. And we are not creating too many false positives, so we had the precision at the level of 54, so this is nice. You can see that the dice is a little bit lower, but it's still very good from the fact that it's very hard even for the experts to say where is the exact boundary of the FCD, because it can also be blending in towards the surrounding tissues. So with that, we're happy. So we thought, okay, so let's do the clinical validation, meaning let's take all of the patients from this moment, and apart from the standard diagnosis that they are having, let's test our model. So we did that. And the results you can see here, I'll just draw your attention to the most important part of it. But first of all, the 3 columns that we have. So the first of them are the neuroradiologists. So these are the experts who are analyzing the MRIs, but they are not specifically epileptologists, so not the experts doing this one narrow field, but they have a little bit broader knowledge. Then we have the ground truth. So all of the ways that we wanted to be sure that our model is, that our ground truth are right. So we know that there were in reality 9 cases. And then are the results of our model. So from this, we can see that our model was able to detect 7 out of 9 FCDs, whereas the doctors were able to recognize 3 of them, which sounds great, right? Like, this is already so big step forward. But if we analyze this a little bit deeper, we can see that whereas we were able to recognize almost 80% of the FCDs, we had the specificity on the level of 5.5%, meaning that our model was very frequently saying that there is FCD where it wasn't, or if you want to use some more buzzwordy things, our model was hallucinating the FCDs in there. So we analyzed it. And what were our key findings? So first of all, if the model was saying that they had 2 or 3 FCDs, it was most probably wrong. It is possible, but it happens very, very rarely. And if it said there is only 1, then it was, in the great majority of the cases, right. Why this happened? First of all, our model was reacting to the artifacts, meaning someone moved a little bit, or there was some other artifacts. It was reacting to some of the characteristics, meaning there was some blurring of the data. I mean, it can be one of the characteristics of the FCD, but it doesn't have to. It can be just some other things happening there. There was also some uneven location of the FCDs, meaning in our data sets, there were some particular parts of the brain in which the FCDs were present more often. So our model learned that because it was just training on the data set that we provided to it. But most importantly here, what happened is that the life was a little bit different. So when we started to take all of the patients that were there, it turned out that not all of them have FCD. Like, as we said at the beginning, it's just 1% of the population, right? So the data distribution was different than the one that we have in our training data set, and that was the issue. So let's sum up this part with the challenges that we're having. So first of all, we have a model that's quite nice at recognizing FCDs, but creates quite many false positives, meaning it is a useful tool, but still to the experts who already have this knowledge, just to have some guides on it, but it's not helping the people who are not expert in this area. Secondly, we have data that were collected only in one hospital, so we have quite low variance of the scanners used. It can be quite obvious, but we are working with the medical data, which are very sensitive, and this will be important for the next part. And it's also connected with, if you ever try to implement any medical projects using AI, you can know that the medical certification regulations are really a nightmare. So there are very, very strict requirements connected with them. So when thinking about what we can do better to improve our model, we more and more frequently were encountering something called continual learning. So we dived a little bit deeper into that, and I would like to explain to you also as well what it is. But before we do it, let's just recap, how does typical machine learning task look like in a simplified way? So of course we start with understanding the problem. We heard today during the keynote, understanding the problem is very important for all software engineering tasks. I would say that for AI even more. We create our data set, as we have already discussed quite a lot today. We train our models, so we test different architectures. Then we have the one that we're really happy with. We deploy it either via an API, or maybe we apply it directly on a stream of data. And we have it, right? So we have functioning machine learning model. So we live happily ever after making inference of our model. Do we? Well, for some time, yes. But what happens quite frequently is that our data will change, especially because of something called the data drift. So there will be different distribution of our data. It can sound quite abstract, but for example, if you're creating a model to detect frauds in financial data, and you have a machine learning model, of course the fraudsters will change their behavior so that you don't catch them. Or if you're like on our example, if you would apply different MRI scanner, the data would be a little bit different. Or if we would be building a recommendation engine, people will change their behavior. Like they will change their preferences, so your recommendation will not be as good as at the beginning. Apart from that, we also, while developing our systems, we might want to add new classes. I mentioned to you that we also use the data of different pathologies of the brain. So you can think like, hey, why don't we, for example, detect as well the brain tumors if we are already having them in the data set, right? Or we might want to add completely new tasks. So for example, we are having a model that is categorizing texts. But it would be also nice if it would be extracting some key information, or maybe it could also do the summaries, which are separate tasks. There will be bias in the data. No matter how hard you try to be as fair as possible and how big data set you are collecting, there will always be some bias. So you always want to be better, meaning that you'll represent some group of the people better, higher, because they are more represented in the data, which will result in some inequalities or some worse performance for some different people. So you might want to increase on that. So just to sum up, the performance of our models will decrease. So we'll want to do something against that, right? And let's analyze a few ways that we have here. So first of them, we can retrain our model using something called transfer learning. And to do that, let's see it on a toy example, or maybe more precisely on a pet example. So let's assume you have lots of pictures of your cats and dogs. And when you're having a bad day, you would like to just see the pictures of your pets and do it quickly. So you train a small neural network to recognize it, and you get very great results. But then the day of weakness comes, and you buy a guinea pig. So now you have 3 pets, but you have your machine learning model that was trained just using cats and dogs. So the sad reality is that whereas it's recognizing them very well, it has no idea about guinea pigs. So you're sad and thinking what you can do. And here is where transfer learning can come to play. So the idea would be that if we have a task that is very similar to what we already had, we could just take the neural network that already knows what cats and dogs are, meaning it already has quite a lot of the important features about like having 4 paws or being fluffy and other things. So we can just reuse that knowledge and feed it with the images of our guinea pig. And we don't need that many because the neural network already knows quite a lot of the common features of pets. So we do that. And we very quickly achieve very great results for our guinea pig, which is great. But in the same time, the performance of cats and dogs is quite abruptly decreasing. So why is that? This is something called catastrophic forgetting. And this is one of the central things connected with continual learning. And what is this catastrophic forgetting? So it applies in the situation when we are training our models sequentially, meaning that we have task number 1, in our case the cats and dogs, which we train and we quite quickly get very great results, whereas the model knows nothing about guinea pigs. And then as the second task in the sequence, we want to take this model and train our guinea pigs. So it gets really great for the guinea pigs, but it very abruptly forgets the information about cats and dogs. And this is really quite serious things connected with the sequential training of the model. And we're going to talk about it more when we get more into continual learning. So, but let's analyze the second strategy that we can have for our pet example. So how about we just train the model from scratch? So we take the pictures of our cats, dogs, guinea pigs, we train the model, and we do it. Will it work? Yes, it will. And we'll get very great results on that. And this is actually the best way to do it in this case. But if we are thinking about other examples, for example, our FCDs, there might be some additional issues here. First of all, we need to keep all of the data. meaning for our pets, we still keep it. But if we are dealing with medical data, we cannot keep the data of the patient forever. If we're thinking about medical or GDPR, because we're in Europe, this is really quite a big privacy concern. Additionally, there is significant costs connected with computation. So when we're training bigger models, if we each time need to train from scratch, that really can cost a lot. And also a lot when it comes to carbon footprint of all of the GPU trainings. And additionally, each training usually takes days, weeks, or even of the large models, it can even take up to months. So it's not always the best solution for all of the problems. But in this situation, there is continual learning which comes into play. So this is the concept that we really can use in this situation, which is also sometimes called incremental learning. So the main promise of continual learning is, and the main idea, that the models should be able to incrementally learn via the sequential manner and adapt to the changing environment without forgetting of what they already learned. Moreover, they should be able to reuse and build on top of the knowledge, like not learn from scratch, but also reuse of what they already know. Does it sound familiar? Like, yes, they should be doing it the way like humans do. And the comparison is not by mistake. And quite many continual learning methods are inspired by biology, which we are going to discover in a few minutes. And because of that, it's like the way how human works. So learning from the experience is also being considered one of the key aspects of intelligence. So if you're looking from the perspective of data, continual learning means that we would like to be able to train our machine learning models via a stateful way, meaning that instead of the stateless retraining, meaning that we take all of the data the whole time, we would like to just train the model once on the data and then just take only a subset of data without using the data that we used before for the initial version of our model. And we have three main methods when it comes to continual learning. First of them is the regularization-based one. The main idea here is that we are penalizing the model for changing the parameters of the neural networks that were causing it to work so well of our previous task. So if you think about neural networks, it's just a set of millions or right now even billions of just numerical values, which are the weights. So the regularization-based method, just the idea here is to keep the ones that were very important for our initial task, to not change them during the training. And there is very interesting idea from biology behind that. So it turns out that the scientists, when they're making experiments on mice, they saw that when mice were learning new things, there were the synapses, so the connections between the neurons in their brain, who are getting stronger. So they're getting less plastic. If there are like any new connections in the brain, they were not touching the synapses when the mice learned a new skill. Whereas in the moment when this connection got lost, got cut, the mice were forgetting the skills. So it means that the brain of the mice was protecting this area of the brain to not get changed to preserve that skill. And the same idea we want to use for the neural networks here. And we use that by adding additional regularization term to the loss function. So meaning during the training for the additional task, so via training a neural network, we usually use a loss function, which we try to minimize. So these are just additional terms that we're adding to this function so that we keep the important information. You might want to ask, like, how do we know which were important? So there are specific ways to do that. For example, Fisher information matrix allows us to detect which of the parameters were important here. But this is not perfect. So usually the forgetting is not fully eliminated, especially if we are having bigger models. And it works usually best if we are having similar kinds of problems that we are trying to solve. Another method, very powerful, is the replay or memories-based method. And the idea is quite simple. Meaning, if we want our model to not forget of what was before, let's just keep some of the data from the before tasks and still keep them in memory buffer when we are retraining for the new task. And this is also quite interesting comparison here when it comes to biology, because this is exactly how our brains are using sleep. So usually when we're sleeping, we are just replaying the activities from the day, so that our brain can consolidate our memories and learn the new skills. And this is why the sleep is so important for the brain, especially for the children who are very experienced and learning a lot during the day. But there are, of course, the issues. So first of all, we cannot keep like as many data as we want in our buffer. And the other one, if you think about it, it still means keeping some of the data in our memory buffer. So it doesn't solve the issue connected with data privacy. But there is a very popular idea over the last months that is being used extensively, which is about using generative models to create this data that we keep in memory buffer. So using the other techniques, we can just create synthetic data, and via this way, we're doing it in a privacy-preserving manner, and still via keeping the models to remember about the previous task that they had. And the last set of methods are the architecture-based approaches. So here, as the name suggests, we are playing with the architecture of our machine learning models, either via adding some specific components, such as additional heads of the models, so the last layers are specific to specific tasks, or via extending our network in some of the areas via additional layers. And the second concept is also called dynamic network expansion, meaning that we're adding additional neurons or layers to allow for the next growth of our network. And this is inspired from biology by the process called neurogenesis, which is creating of new neurons in our brain in the areas where they are needed next. So this is especially happening in hippocampus here. But the assumption here is that we should know the clear task boundaries so that we can use it, which not always is really doable. So let's jump now back to our FCD story, and let's see how continual learning can be applied in a real-life task. So we came back again, having all of this knowledge about continual learning, and we again decided to collect a new data set. But this time, we wanted to adapt it to the real-life data distribution, meaning that the FCD are not in the majority. It's the other way around. Right now, we only had 10% of the FCDs in our data set. So we had the 30 FCDs MRIs with FCDs, 150 normal, and 120 other than FCDs pathologies. And we divided it into 3 separate data sets. And let's take a look of which of the methods of continual learning did we use. So because we are having the change data distribution and we're having a new task, but which is still very similar to what we had before, we are starting with the regularization-based approach, more specifically elastic waste consolidation. And by the way, a best practice in here, so regularization-based approach is the easiest one of them all, and it is recommended to start with it, and only if it's not helping, move forward to the other methods. So having the data sets, we have started our training. And let's take a look at the phase 0, which is our starting point, just a revision of what we said in our act number 1. So we had our baseline data sets, we trained our neural network, we have our baseline model, and we just keep it there. So phase 1 means we are taking the first of our 3 data sets, so the 100 MRIs where FCDs are just 10%. In the first step, we are just taking the model that we trained before, and we are just evaluating the results. Later, we had 2 training strategies. So first of them means that we wanted to compare what if we kept the data for some time. We had, of course, the permissions to do that. But we wanted to be sure, like, if the models will be better, worse, or if there will be any significant changes. So here we just assume that we take all of the data we had from the beginning, meaning we had the baseline data set, and we also added the 100 MRIs that we have now. We trained our neural network, and we had the model. Here it's quite fancy name because we're also writing scientific paper about it, but we don't need to be fancy right now, so let's just call it all data model. And the second one was connected with continual learning, which means we are showing to the model only data from this training stage, meaning it only sees the 100 MRIs, it doesn't see all the baseline data set. And we're also training here using the regularization parameters, the next models, which you are calling here continual learning. Phase 2 means that we take our data set number 2, and we are here, first of all, comparing our results. So we have the baseline model, the all data model, and the continual learning one. We save the results. We'll take a look at them in a minute. And then, again, we are repeating our training strategy, meaning for the all data 2 model, we're again taking all of the data that we're having from the beginning. So we have the baseline, dataset number 1, dataset number 2. We are training the model, and we are calling it all data 2. And for the continual learning approach, again, we're just feeding it with the dataset 2. It doesn't see the dataset 1, it doesn't see baseline dataset, it just sees this data, but it's continuously trained on our previous continual learned model. So we have like the chain of tasks here. And for the dataset number 3, we can only evaluate the data. So we are checking it against the baseline model and the 2 newer versions that we have. So let's take a look at our results, which look like that. For the baseline model, it behaved in a very similar way that it did before, meaning it was able to detect in a phase 1, 2, and 3, 8 or 9 out of 10 cases of FCD, which is very useful and great results. But it still was having very low specificity. What we have seen in the old data, meaning that we have changed already the data distribution here, it still recognizes very well the FCDs, having 8 and even 10 out of 10 FCDs correctly recognized. And it is already getting much better on the specificity, which we can see that it's increased to 56. And let's take a look now at the continual learning one. So we are still having the sensitivity of 8 or 9, so still comparable with the baseline model. And we also discussed with the epileptologist that the difference between the having 10 and in the other cases 9, assuming this amount of data, this is like not a big difference. So we can say that all of the models were having very comparable results on the sensitivity. But we have seen that we achieved even 70% of specificity. So our model was very good in also not creating the false positives here. We, of course, also analyzed a bit the behavior here, and the additional observation were that if still our continually learned model was creating these false positives, it was, in the majority of the cases, just recognizing these other brain pathologies. So if you would like to have a really great scientific paper claiming that we're great, we could just remove that and claim that we have 90% of specificity. And as the training progressed, so as we also included more different data with non-FCDs, we have also seen that right now we don't have issues connected with like detecting FCDs in one particular area of the brain, which is great. So summing up, we have a very similar level of sensitivity, which we just said. We have significantly higher specificity compared to the baseline model, and something that is not so obvious from the data that we just see, which is that we believe that the continually learned model will be much more robust for the further data distributions. If you think about it, like if we really continued to train the data on the real-life examples, meaning at the end there will be just 1% of the MRI scans, because like the majority of the population doesn't have FCDs. At some points, it will be similar kind of problems as we have with detecting anomalies, for example, in machines, etc., meaning the model would be likely to say there is non-FCD, and it will be right in 99% of the cases, right? Because it's just adapting to the data distribution. So what we think is very strong here for the continual learning area is that we first train the model to recognize these very subtle changes. So it's very good at recognizing this task. And later on, we are still making it remember it. So even if the data distribution will be changing, it will still know and keep this knowledge about what are the specifics of these FCDs. And via using this method, it will also be better into the changes in distribution in the future. So at the end, we managed to create a model that is considered being useful for the daily clinical practice for detecting FCDs. And to sum up this talk, so we have seen that neural networks tend to forget old things when we train them sequentially on the new tasks. And this is called catastrophic forgetting. We have also learned that continual learning is a set of methods that allows us to fight against it and to keep learning from the new real-world data without forgetting previous skills. We have also seen that there are different kinds of methods. So we have analyzed, on example, the regularization-based methods, but there are also other ones which can work better in different cases. Another thing is that we have seen that they are also quite useful niche AI applications other than writing code, emails, or generating Ghibli-style pictures. And one of them is using machine learning to help expanding the access to epilepsy surgery and improving the diagnosis of drug-resistant focal epilepsies. If you would like to learn more, especially about our data set, about the details of the neural network, and about our results, we have published 2 scientific publications in epilepsy research, which is one of the most renowned journals when it comes to epilepsy worldwide. I also had a thought that probably machine learning is one of the areas in computer science where you can still write scientific papers, and it's quite normal. But yeah, I encourage you to take a look if you want to learn more. But I told you there will be 3.5 acts. And if you listen carefully, I also said that there will be no LLMs in this talk. Well, let's say that I lied a little bit here. But I have a talk when preparing it. I thought while preparing this talk that probably if you will be hearing about all of this, like it has a great potential of not having to retrain the models, and because training of the models can really take months, etc. So what would be the benefits for LLMs to really use this kind of methods? So the results are that according to what I found on the internet, none of the big providers of the LLMs is using continual learning. Why is that? Because it's not so easy. If you were in any of the talks about large language models, you probably have seen that it's not as straightforward as just training one model and that's it. It's actually a sequence of different kind of trainings. So we have the pre-training, so training on the large amounts of data, such as on the internet. Then we have the instruction tuning. So we have another training where you want the model not to just predict the next word, but also to follow the instructions that we have. And thirdly, we also have additional training, which is connected with the adaptation. So we want our model to comply and to behave in a way that is in line with human values. And what it turns out that for each of the stages, we can continuously train them. But the tricky part here is that if we try to tweak one of them, it can have a little bit unpredictable impact on the other areas. So that's why it's not in common use in there. But if you're really interested in that, there is really a lot of it happening in the research. If you would like to learn more, you can reach out to me later. I can point you to some nice resources in this area. But to sum up on that, I do believe, like, especially as we said that actually continual learning, so adapting, learning from experience, it is something very important if we want to try to build truly intelligent systems. So learning from experience without forgetting, it's not something nice to have. is really, really important if we want to develop the intelligent system. So I do believe that may it be LLMs, may it be completely different architectures, but if you would like to build truly intelligent systems, I do believe that continual learning will be one of the big leaps that we'll see in the future and delivering on the promise of it. So with that, thank you a lot. I hope you learned something and have a nice rest of the conference.